we continue, I want to do a little more explanation here. Remember, I mentioned in this equation, first we get this is one solution. Okay? This is the second solution. Why? After we get two solutions, we add them up. It is still a solution. Yeah, that property we call the linearity property. Linearity property. So what kind of equation has this linearity property? Not everyone. Yeah. So for equation to have this linearity property, it should be equation like this has that property. So what kind of equation? Homogeneous linear equations. Homogeneous linear ODEs. Okay, so what's homogeneous? Other than the y terms, then the right hand side is 0. When the right hand side is 0, we call it homogeneous. If the right hand side is f function not equal to 0, then it's not homogeneous. Okay, but this side must be 0. So then the linear, I think you know the linear, right? Linear, no square. Okay, no square term, no, only the linear. So with respect to y, linear function. With respect to y double prime, also linear function. Yeah. With respect to y prime, also linear function. Yeah. 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 So in our module 2, we will talk about that. Homogeneous linear equations, ODEs. Yeah. Yeah. All right. Yeah. Yeah. Let's continue. Example. We almost finished number 6. Now we can write u of x, y equal capital A, capital B, capital A of x, capital B of x. Yeah, similar to that way. Yeah, arbitrary functions. Yeah. All right. Yeah. So we finish example number 6. Then our last example of this part. Yeah. Example 7. Solve the first order ODE partial u over partial t plus constant c, non-zero constant c times partial u over partial x equals 0. Yeah. So there is a name for it. Advection equation. Yeah. Yeah. It is very simple, but we need to use a special way to solve it. All right. Recall the chain rule. Here, we need to use the chain rule. Yeah. All right. So let's consider the special. So this u function with two variables, t variable and x variable. But here, many times when we solve some problems, we need to use our imagination. Okay? Yeah. So you can do many assumptions, but your assumptions should be reasonable. If your assumptions are not quite right, so then sooner or later you get stuck. Yeah. If your assumptions are along the right direction, then you can get through. Yeah. Here we want to make reasonable assumptions. What's the assumption? We assume this u function is a composite function. Yeah. Chain rule composite function. Yeah. F of f is a one variable function, okay? But that variable inside f, it's a another function, g function of t and x. That's the assumption. That's the imagination. In problem solving, many times we need to use our imagination. Yeah. Yeah. So that's the part. Human intelligence and AI different. So we human, we have imaginations. Yeah. So AI, doing things differently. Yeah. All right. So here, that G function. Now we need to consider G function. Yeah. For the G function, because a lot of uncertainty in G function, right? What's the G function? A lot of things uncertain. Yeah. Then, a lot of uncertainty, that means we have a lot of freedom to choose the specific form of G function, right? We have freedom to choose the form of G function. When we have freedom to choose something, usually we want to choose relatively simple function, right? Yeah. Because if we choose simple functions, the calculation will be easier. So we don't want to make our function unnecessarily complicated, right? Too complicated. Yeah. We want to make our lives easier in this situation. So what function can you imagine as simple function? Here. Yeah. We have freedom to choose G function, and we want to choose simple G function. So now you need to try some simple G function. Linear function. Is linear function simple? Linear function simple. Yeah, let's choose G function, linear function. G of t comma x, at plus by, at plus bx. A, b are certain constant to be determined. We have freedom. A, b, what are your A and B constant? To be determined. That's also our freedom. That's the freedom we can choose. Yeah. All right. When you do this assumption, now you can apply chain rule. Apply chain rule on U function, right? Yeah. Chain rule on U function. Yeah. All right. By chain rule, what is partial U over partial T? Partial U over partial T. Okay? Yeah. First, we take derivative on F. dF over du. Because F is a one variable function. So we take derivative on F. One variable function. U. Okay? Then, inside chain rule, partial G over partial T. Partial G over partial T. Partial G over partial T, that's A. Second term is gone, right? When you take partial G over partial T. Second term is gone, that's 0. So first term is A. Okay, all right. So you get A times dF over du. Chain rule. Then let's take partial U over partial X. Another chain rule. dF over du times partial G over partial X. partial g over partial x, first term is gone. Partial g over partial x. Second term is b. When you do partial derivative, it's b, right? So we get b times df over du. Two partial derivatives. Now we want to go back to this equation. Because we have the expression for the first partial derivative, we also have the expression for the second partial derivative. So let's calculate partial u over partial t times c plus c times partial u over partial x. Yeah. Partial u over partial t, let's copy. A times df over du df plus second one, yeah, because you have a c there. So b times c times df over du. All right. Then, now, in this expression, remember a, b, two constant to be determined. We have freedom to choose the values of a and b. We have a lot of freedom to choose the concrete values for a and b. And we want to make our life easier, right? Yeah. We want to choose the best values we can think about. Yes. All right. The first one, make b1. Well, yeah. That will be simpler. So the first, b equals 1. So let's simplify the first round. A and C. C is a fixed constant. You have no freedom to do anything on it. Yeah? So you need to keep that C, but we have freedom on A, right? Can we choose negative A as negative C? Then cancel out. So our second round, because we have freedom, we can choose A as any value, right? Any constant value. So we use that freedom, but this time we choose A equals negative C. If A equals negative C, cancel out, right? Positive term, negative, gone. Gone, that means 0. 0, that satisfies our original equation, right? See? Our original equation is satisfied. Yeah. That means now, when we choose b equals 1, a equals negative c, that means when we choose g function as this linear function, x minus ct, we find the solution form for the original equation. Okay? Yeah. So in that case, composite function, u function can take f of x minus ct. Yeah. And f here, because you need to take derivative of f, right? df over du. So f must be a differentiable function. Yeah. For any differentiable function, f. Yeah. You can use any differentiable function, little f here. Then you make u function as f of x minus ct, so it is a solution of the original equation. Yeah? Yeah. Yeah. All right. Here you can see for PDE, yeah, so our techniques are quite different. Yeah, we need to use many different techniques to solve PDEs. Yeah, much harder than ODEs. Yeah, yeah, but this is the first time. Yeah. So at this point, so we finish. Finish part C. Yeah, this our first PDE topic. Yeah. All right. Now I need to change to different part D. Yeah. So I have half an hour, so I can, cover some topics in part D. exact ODEs. D.1, exact ODEs. And in this topic, we need to use partial derivatives. Yeah, partial derivatives. Yeah. All right. Let's look at the question. So we need to develop another tool for solving ODEs. Yeah. All right. Technique. Yeah. Recall the explicit ODE form. Yeah. Yeah. So this is the very general. Yeah. But this is too general. Yeah. We want to consider some special ODEs. Here, the special ODEs should have some special structure, because we need to use that structure to help us solve the ODEs. What kind of special structure? Y prime equals a fraction. So the f function has this fraction form. Okay, yeah. Numerator, capital M, two-variable function. Denominator, capital N, two-variable function. Yeah. So we consider ODE with this special form. Why we consider this special form? Yeah. 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 Some mathematicians, due to some reasons, they discovered this technique. Yeah. All right. Yeah. Consider. Yeah. Because y prime equals dy over dx. Consider this equation. Yeah. Here, when we write dy over dx, differential. Here, we use differentials. We want to separate them. Separate dy and dx. Separate them. So we get a differential form. Yeah. So here, we need to use differential concept here. All right. All right, special property. So let's study some special property. This special property is called total differential concept. Yeah. Differential, we know differential. Yeah. But here, a special type of differentials called a total differential. Why you call it total differential? Yeah. So let's look at the situation. Yeah. Consider an explicit function or curve with the form. Yeah. Here, let's consider general form. U y equals c. This function. Yeah. Actually, this function we call it implicit function, not explicit. Yeah. So I think this word, should be implicit function. Yeah, because this function we call implicit function. Not the explicit. Explicit should be y equals f of x. This is explicit function. Implicit function, because we mixed x and y, we cannot separate x and y. X, y mixed, hard to separate. So we keep the mixed form. Yeah, that's the implicit function. All right. One simple example of the implicit function. X squared plus y squared equals 1. This is well-known equation for a circle, right? Yeah. Well-known equation for a circle. All right. Then, in this simple example, can we take differential both sides? Differential, d. So we take d operator both sides. D. We treat d as an operator. Okay? Operation. D is an operation. Differential operation. We apply differential operation both sides. D. Okay? All right. Yeah. Then, for example, if we work on this version, left-hand side we take differential, that's du, right? Du. Right-hand side, d constant, that's 0, right? Yeah. Differential on any constant, it's 0. Yeah. Because derivative of constant is 0. Yeah. Derivative times some differential, yeah, but the derivative is 0. So du equals 0. Okay? du equals 0. Yeah. All right. Then, now we need to get this concept, total differential concept. Why you call it total differential? All right. Yeah. All right. Du, when we take du, we can write, yeah, because this u has two variables. Du, remember, in our part C, we have one formula, differential formula when we write, but in that formula we use 3 variables. Here 2 variables. Okay, that variable, that version I remember x, y, z, f of x, y, z. But here, yeah, we have 2 variables, so we write 2 variable version. Du equals partial u over partial x times dx. Dx differential. Okay, but there is a partial derivative. Multiply dx plus partial derivative, partial u over partial y, times dy differential. Okay? Yeah. Yeah. So we have this formula. This formula now related to this total differential concept. Related to total differential concept. Why? We call it total differential concept. All right. Now, let me cover this. You only look at this side. When you look at this side, it's a differential form, right? Sum of 2 differentials. It's a differential form. All right. This differential form could be various different forms, right? Yeah. See it? Arbitrary forms. Arbitrary differential form. This form may not be able to, you may not be able to written as a du, right? Yeah. Sometimes, yeah, so, yeah, all right. So let me write, I should say in this way, otherwise you get confused. All right. Let me write a x y times dx plus b x y times dy. This is a very general differential expression, right? Yeah. For this general differential expression, can you find du equals that? In general, you cannot. In general, you cannot. Because arbitrary a function, arbitrary b function, how can you find some u function such that du equals that function? In general, you cannot. Only under some very special situation. If you are very lucky, yeah, some special condition is satisfied, then you can find appropriate u so that du equals that one. But if you can find appropriate u such that du equals that, we call that differential as the total differential. If you cannot find such u, we cannot call that it's total differential. Yeah. Because this du is the total difference. But du, very obvious, right? Du is a one differential. But when you look at that differential form, it's not obvious, right? Yeah, it's not obvious. It's not obvious you can find a u such that du equals that. Yeah. But if you can, we call this differential expression as a total differential. That's this concept, total differential. Okay? There exists such u. Yeah? Yeah, but this form is a total differential. Yeah? Because this form equals that du. So this is total differential. No problem. Okay? Yeah. All right. Yeah. So now you understand this total differential concept. Yeah. Here, when we go back to this form, m function, n function, then, because n function arbitrary function, n function also arbitrary function, then you may not get a total differential, right? Yeah, so that's the point. Now, let's write the differential form. Yeah. Yeah. Let's convert this original equation to the differential form. This is the differential form. Okay, differential form. But this differential form, left-hand side, yeah, m arbitrary two-variable function, capital N arbitrary two-variable function, it may not be total differential, right? Yeah. In general, it's not total differential. If it's not a total differential, then we cannot solve it. We don't know how to solve it. But if it happens to be a total differential, then we can solve it. That's the point. If it happens to be the total differential, then we can solve it. Yeah, that's the point. So now we only consider those capital M function, capital M function, such that this left-hand side is a total differential. Then we can solve it. Okay? That's this method. All right. Now, here it's a negative sign. Is it important? It's not important. Yeah. Because n is an arbitrary function. N is arbitrary function. That negative sign we can put in an m part, right? Yeah. So we consider plus version. Because negative sign, we put it inside n function, n arbitrary function, right? Yeah. Because the reason we make the negative sign there to plus sign, look at it. The total differential form is a plus sign, right? Yeah. Because our goal, we want to make this differential as some total differential. That's our goal. Yeah. So we want to use plus sign here. Okay? All right. All right. Yeah. Then the corresponding ODE becomes negative sign now. That's okay, right? Yeah. We modify slightly the original equation. Yeah. All right. Then, now, our goal, we want to make this differential form as a total differential. That means we need to find some u. Yeah. It's unknown. Here, the u is unknown. Such that partial u over partial x times dx plus partial over partial y times dy equals that. And the question, we want to see if it's possible or not. If it is possible, then we find a solution. If it's not possible, then this method doesn't work. Yeah. Doesn't work. We need to try different methods. Yeah. This one doesn't work. Yeah. All right. Criterion for exact differential equations. All right. Exact differential equations. Yeah. So when you see this differential, this form, yeah. So we write our ODE in this special form. Yeah. Okay? Yeah. Sometimes we like to write in this way. Yeah. All right. How do you know if there exists a U function such that du equals that expression? Okay. Yeah, total differential. Yeah. All right. There is some criteria. We want to see what's that criteria. Okay? Yeah, what's that criteria? Yeah. All right. All right. Yeah. So here, because this U here, we consider solution in this form. Yeah. So the solution for our ODE is in implicit form. Yeah, here, implicit form. This is implicit form. It's not explicit form. Okay? Yeah. The solution, yeah, this time, we consider the implicit equation, implicit function. Yeah, let's call it implicit function. Okay? This implicit function is the solution of that ODE. Yeah. All right. We consider this case. All right. All right. So now, yeah, to make this differential form as a total differential for some unknown U here unknown U. All right. Yeah. So we need to determine. First thing is, we need to see if such U exists or not. It may not exist. U function may not exist. So we need to find the condition. Under what condition the U function exists? That's the question. That's the criteria for exact differential equation. Yeah. Yeah. If you can represent as a total differential, then we call that equation is the exact differential. That equation, exact differential equation. Yeah. All right. Yeah. Such that, so here you can see, yeah, if you compare these two sides term by term, so capital M function should be corresponds to partial U over partial X. Capital M function corresponds to partial U over partial Y. Yeah. 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 All right. Yeah. So now, the question, does it exist U function such that you have these two equations? Yeah. All right. Yeah. There is a critical property here. Yeah. Yeah. We learned in part C. Yeah. It's this one. The two mixed partials the same. That's the Claris theorem, right? Claris theorem. That's, when we change the order of the partial derivative, yeah, the same. But this equality is true under certain condition. There is a condition. Yeah. There is a condition. What's that condition? Yeah. 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 We will see that condition later. All right. So look at that. Yeah. Assume we have this equality. All right. Then you take partial M over partial Y equals mixed partial derivatives. And partial N over partial X, another mixed, but in different order, right? Yeah. Here, different order. But based on this property, they should be the same. So the criteria, in order to find such U, this must be true. You need to check this condition. If it is true, then it's possible to find U. But you don't know how to find. Yeah. It's possible to find such U. Yeah. You need to figure out how to find such U. Yeah. All right. But at least you get the criteria here. If this equality does not hold, then this method does not work. You cannot find such U directly. You cannot find such U directly. Yeah. Yeah. All right. Yeah. So this condition, we can check it easily. Yeah. Because m function is given, we just calculate these two partial derivatives and compare. Okay. Yeah. All right. Yeah. Then condition. Now let's review that condition. Yeah, we learned before. Let's review. Under what condition this equality holds? Yeah. These two partial derivatives continuous. The mixed partial derivatives are continuous. On some disk D, remember? Yeah. So on some disk D. Yeah. 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 So that's we learned some theorem. Yeah. Yeah. Clara's theorem. Okay. Yeah. All right. So then we have that criteria. Yeah. All right. Yeah. Yeah. Next question. Suppose this equality holds, how do you find U function? Yeah. Yeah. So, antiderivative, right? Antiderivative. Yeah. Think about partial U over partial X equals this function is known, given. Can you do antiderivative with respect to X to get at least partial information of U, right? Yeah. Can you do antiderivative with respect to Y to get a partial information of U? You combine those two partial information, can you find the final solution for U? Yeah. 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 We can do it that way. All right. Next. Let's find U. Yeah. Yeah. This time, we assume we have that equality. Yeah. We have that. Yeah. So we can say, we have the exact ODE. Yeah. So that condition, yeah. That condition guarantees the corresponding ODE is exact. All right. For this equation is exact, okay, with that condition. All right. Solution. Now, let's calculate. Yeah. All right. All right. Antiderivative. All right. Yeah. Yeah. So we have these two equations. We need to find a U satisfy both equations by antiderivatives. All right. All right. The first antiderivative, U integral m function with respect to variable x. Then the constant part, yeah, there should be some constant part, right? Constant part unknown, so we use a little k function, k of y, to represent the constant with respect to variable x. Yeah. Yeah. K function, little k function, to be determined later. Yeah. Similarly, we work on the second equation, okay? Antiderivative with respect to y, u of x comma y, integral of m function with respect to y variable. The constant part, we need another function, little l function, with x as the variable. Yeah? Yeah, because we treat x as constant in the second form. All right. Then same U function should satisfy both forms. Both forms. Yeah. All right? Yeah. Yeah. But these two functions could be determined. Could be determined. All right? Yeah. Here I describe the way to determine. Yeah. Yeah. All right. All right. How to determine K function and the L function. Yeah. So here we apply some. We take partial derivatives on the first formula and second formula as follows. Yeah. First one, we take a partial U over partial Y. Yeah. Not over partial X. Yeah, partial Y. Because partial Y, we need to take a derivative of little k function. Okay? Yeah. The second one, we need to take partial U over partial X. So we need to take derivative on little L function. Okay? Yeah, little L function. Yeah. All right. Yeah. When we do that, yeah, on formula 1, K prime equals that. Yeah, because this expression can be calculated. This function is known. So that means your little k function is known. Yeah. Yeah. From this equation, you can get a k prime of y is known. Can you find the k prime? Antiderivative. K prime is known, so you can find the antiderivative of the prime. You can get a k function. Yeah. Similarly, on the second one, you take derivative. Yeah. You take this partial derivative. So you get an L prime function, and this is known, this is known. So L prime function is known. So you take antiderivative, you can find this little L function. Okay? So these two functions can be determined in this way. So you can write out the final U function. All right. Yeah, but here, yeah, because let me finish this slide with some comments. All right. The method is here. Yeah. So if you can follow, you can understand. You can use this method. Yeah. But in our calculation, actually, there is a simplified way to find a U. Simplified way. Yeah. Yeah. And we do not need to do antiderivatives here and there. Remember, we did an example before. We find a common umbrella. Remember? Common umbrella to cover two different forms. Yeah. We use that idea. We do not need to. We can skip this step. We can skip this step. We work on these two formulas directly with that, common terms, keep common terms, and copy different terms, common umbrella way. Yeah. Next time I will use some concrete examples to show you that simplified version. The simplified version, we can skip these two steps. Okay? We can skip these two steps. Yeah. We write a U final solution directly from these two formulas. Yeah. All right. All right. So let's stop right here. Today, yeah. Next time we need to complete this part. Yeah. Yeah. But I have another part. So our module 1, this is part D. Yeah. But I have part E, another part. Yeah. But this week, let me remind you, this week, exercise set part, I need to post solution. Then post a new set of exercise questions. Then I also need to post the quiz 1. this weekend. Quiz 1. And give you 1 week to complete. Quiz 1, yeah. I forgot to mention in my syllabus part, I didn't say how long, right? Yeah. 1 week. At least 1 week. Yeah. A little, could be a little longer. Yeah. Well, yeah. Question?
Can you remind me of what day, when are homework assignments typically due? Is it like Thursday or
Sunday. Quiz always end of Sunday.
and homework?
Homework, not necessary. Homework, yeah, could be different.
I mean,
Yeah.
I usually work on stuff over the weekend, so
Yeah.
ideally, if it's like,
You like weekend? You like?
that's the only time I have really.
Yeah. Weekend, I try to make weekend. Yeah. I try to make weekend.
That'd be great. Yeah.
Yeah. I haven't posted. Yeah. I haven't posted. Yeah, but could be, let me try Friday. Friday, yeah. If Friday I couldn't find time, then early Saturday. But the deadline, end of Sunday next week.
Okay.
Yeah.
And the exercises you're talking about are practice.
Practice.
Okay.
Self-study. So no submission. Yeah.
Okay.
Yeah.
Thank you.
Mm-hmm.